So hello guys, in the previous video we saw how to derive a dimension formula. So in this video we are going to look at 40 plus, just a second, 40 plus dimensional formulas. Okay. So we're going to take more than 40 plus physical quantities and derive the dimensional formula for each and every quantity. Okay. So firstly, let us start with area. So area of a square is a square. So a is the side of the square. Therefore, it is a measurement of length, due to which this will be the dimension formula of area will be L square. Okay. And then we will see volume. So for example, volume of a cube is a cube, as you know. And a is again the side of the cube. Therefore, the dimension of volume will be L cube. Thirdly, density. So density is mass by volume. So mass is m, volume is L cube. So this will give me ml to the power minus 3. This is the dimension of density. So if you have any doubts, like what is L, what is M, you can go refer to my previous video where I have explained in detail what are those fundamental quantities and why do we write dimension formulas like this. So if you have any doubt in that sense, you can go visit my previous video. And next we'll look at speed, which is distance by time. So that implies, so distance is a measurement of length, therefore it is L, time is t. This gives me speed as Lt minus 1. Velocity also has the same dimension, therefore you can write it as speed or velocity. Okay. Next we'll look at acceleration. So acceleration is velocity by time. Okay. So therefore I can write velocity's dimension to be Lt minus 1 by t. This gives me acceleration's dimension as Lt minus 2 to the power minus 2. Okay. So this is acceleration. Next we will look at force. Okay. So force F is equal to ma, where m is mass, a is acceleration. Okay. So from this we can write mass and acceleration dimension we have derived it to be Lt minus 2. Lt minus 2. So this gives me mLt minus 2 as the dimension of force. Then we can look at, so next we have work. Okay, work is force into displacement. Force into displacement, which is Fs. So I know what is force. I know it is mLt to the power minus 2. I know displacement is a measurement of length. So from this I can get it as ml square t to the power of minus 2. So you can also keep it as work or energy. So it is either work or energy, both have the same dimension. Work, energy. So energy includes potential energy, kinetic energy, or any other form of energy. All have the same dimension of ml square t to the power of minus 2. So if you're confused, how come potential energy, kinetic energy all have the same dimension, we can maybe derive for these quantities. So if you consider potential energy, this has the formula mgh. You might have learned this in your ninth standard. So m is mass, g is acceleration due to gravity, and h is height. Okay. So I know mass is m, acceleration due to gravity is Lt minus 2 again, because it is a form of acceleration, and I've explained why are acceleration due to gravity and normal acceleration are same in my previous video. You can refer to that. And height is a measurement of length, so I can put L. So from this I am getting ml square t to the power of minus 2 as my dimension for potential energy. Now if I look at kinetic energy, this has a formula of half mv square. Okay. For dimensional purpose, I don't consider constants. Okay. And m has dimension of m. V square is Lt minus 1 whole square. So from this I can write it as ml square t to the power of minus 2. So this proves that all the potential energy, kinetic energy, or any other form of energy has the same dimension as work. All these are same. Okay. I hope you understood this concept. Next, we look at power. Power is work done by time. I know what is power work. It is ml square t to the power of minus 2. I know what is time, which is t. So from this I get power's dimension to be ml square t to the power of minus 3. So this is power. Then we can move on to pressure. So pressure is force by area. I know what is force dimension. It is ml t to the power of minus 2. Area is L square. We have derived both these previously. I can cancel Ln square. So now I get pressure dimension as m L inverse t to the power of minus 2. Okay, for a note point, you can add stress also has the same dimension as pressure. Okay, and not just stress, modulus of elasticity. Modulus of elasticity. E. So E includes Young's modulus, bulk modulus, rigidity modulus. So this is Young. It is fine if you don't understand these concepts because you will be learning all these things in the later part of your curriculum. Bulk modulus, rigidity modulus. You can just understand what are these in basic sense in the dimensional point of view. So all these physical quantities have the same dimension as pressure. Okay, as pressure. The purpose for me to give this is that maybe in your examination point of view, they might ask you a question: which of the following physical quantities have the same dimension as pressure? And the option they might give you stress, and then linear momentum, force, energy. Okay, then you should be able to tell that stress has the same dimension as pressure because from this note point you can understand. So then comes linear momentum. Linear momentum. Okay, you have learned this what is linear momentum in the 9th grade, which is mv. Okay, mass into velocity. I know mass is m. I know velocity is lt minus 1. Therefore, this is mlt minus 1. Okay. So, there is another physical quantity known as impulse, which is ft, force into time. Okay. So, if I derive the dimension of impulse, it is mlt to the power of minus 2 into t. That will give me mlt minus 1. So, from this, I can verify that linear momentum and impulse has the same dimension. There is a lot of effort that is going into finding what are all the physical quantities that is same to each other dimensionally. So in case if you find this video to be valuable, make sure you subscribe to my channel and also like this video. Okay, next we can move to 11th physical quantity, which is acceleration due to gravity. I've derived this in detail in my previous video. So this comes from a formula T is equal to 2 pi root of L by G. Okay. So when you are calculating the dimensional formula, we don't consider constant, so we will cancel this. And from this, you will finally get this as LT minus 2. You can maybe try this out. Okay. Then we have universal gravitational constant. I've also derived this in detail in my previous video, so make sure you watch that. So F is equal to G m1 m2 by r square. So G is the universal gravitational constant. This is universal gravitational constant. F is force. This is mass 1, mass 2. These are masses. And this is radius. Okay. So from this we can derive G to be m inverse L cube T inverse 2. I've derived this in detail in my previous video. Then we have frequency, which is 1 by time period. From this, I can derive its dimension to be t minus 1. So now I'd like to make, so before moving on to our 14th dimension physical quantity, I would like to make a point, note point. Angular displacement coefficient of friction relative density Reynolds number. These are all dimensionless quantities. They don't have any dimension. Which means, in case if they ask you what is the dimension of coefficient of friction, you must write it as m0, l0, t0. So anything raised to the power 0 is 1. So they don't have any dimension. All these quantities, they don't have any dimension. So now let us move on to our 14th physical quantity, which is angular velocity, omega. So this is del theta by del t. So del theta is angular displacement. As I have mentioned before, that angular displacement doesn't have any dimension. Now it is very easy for you to find the dimension of angular velocity. So it is just 1 by t, which is t inverse. So omega is t inverse. Okay. Then I have angular acceleration, which is alpha. This is del w by del t. So I know omega is t to the raised t inverse. So by t, therefore I'll put t over here. From this I can get angular acceleration's dimensions to be t raised to the power minus 2. 16th physical quantity is going to be wavelength. So the name itself suggests that there is some type of length. Okay, even if you don't understand what it is right now. So this has the dimension of L. 17th. Angular momentum. Okay, L represented by L. So don't confuse this with the base fundamental quantities of length. Okay, angular momentum is generally represented as L. So if it is confusing, just leave it. So this is a formula of MVR, mass into velocity into radius. Okay, so mass into velocity is LT minus 1 into radius is a type of length, so I'll put it as L. So this is ml square t to the power of minus 1. This is the dimension of angular momentum. Then we can look at Planck's constant. So there is a formula, energy is equal to hf, okay, where h is the Planck's constant. So f is frequency, E is energy. Okay, so from this it is very easy for me to write the dimension of h. H is equal to energy by f. I am just rearranging the formula. So from this, energy is ml square t to the power of minus 2 and f is t inverse. So I am basically getting ml square t to the power of minus 1 as the dimension of Planck's constant. Now these two, angular momentum and Planck's constant, have the same dimension. You can verify this over here. ml square t inverse, ml square t inverse. 18th, surface tension. So surface tension is basically, it's fine if you don't understand what is surface tension, it is force by length, okay, which is mlt raised to minus 2 by L. So L gets cancelled. So finally it is, you will remain with mt raised to the power minus 2. So this is the dimension of surface tension. Then we have coefficient of viscosity. So there is a formula. F is equal to eta A del V by del X. Okay, where eta is the coefficient of viscosity. A is area of cross section. So some sort of area, doesn't matter what area, it is some sort of area. So this is velocity, this is a measurement of length. Okay, this is force. So if I rearrange this formula in terms of eta, that will be eta is equal to F by A del V by del X. So F by A is pressure, force by area is pressure. Okay, it is fine if you don't understand what is this del V by del X. Just listen to what I'm telling. So this is velocity, this is length. Okay, this concept, whatever I'm teaching you right now, is basically to let you know how to derive dimension formula of any dimensional formulas for any physical quantity. That is the goal of this video. It is not into explaining what is this coefficient of viscosity, what is viscous force, etc. Okay. So eta will have, yeah, pressure's dimension is m L minus 1 t power minus 2 by, I told you that it is velocity by length. So this will get cancelled. So finally you will have m L minus 1 t minus 1. So this is the dimension of coefficient of viscosity, eta. Then you have, so we are halfway done with 40 physical quantities. Now 21st, it is velocity of light, which is represented by c. Since it is velocity, you need not worry about anything. The dimension will be Lt minus 1. Heat capacity. Okay, so heat capacity is denoted by H, which is equal to dq by dt. Let me just explain. This is amount of heat energy change in temperature. Okay, see, this is heat energy. dq is heat energy. So energy, any type of energy will have the dimension formula ml square t raised to minus 2 by change in temperature. So temperature is a fundamental quantity, therefore it has the dimension K. Okay, Kelvin. There are 7 fundamental quantities as we have discussed in our previous class. They are length, mass, time, then temperature, electric, amount of substance, and luminous intensity. So temperature is a fundamental quantity, therefore we are bringing in K right now. Okay, from this we will get H is equal to ml square t minus 2 K inverse. Therefore the dimensional quantity of heat capacity is ml square t raised to minus 2 K inverse. Then we can move on to specific heat. So these are all the formulas that you will be learning as part of your curriculum moving forward in your class 11th and 12th grade. Therefore, it is fine if you don't understand all these things right now. Because once you learn those, this will be very helpful and you will have a better understanding about all these things. So this is 1 by m dq by dt. So 1 by m, this is mass. Okay, this is mass. And we know what is dq by dt. So dq by dt, we have derived it as our heat. This is heat capacity. Therefore, you can just put in this value over here, which is ml square t minus 2 k inverse by this is mass. So mass will get cancelled. So the dimension of specific heat is derived to be L square t raised to minus 2 k inverse. This is the dimension of specific heat. Then you have latent heat, which is denoted by L. So the formula for latent heat is Q by M. So Q, as I told you before, this is heat energy. M is mass. Okay. So I know any type of energy will give me ml square T raised to minus 2 by M. So M1 will get cancelled. Therefore, latent heat has a dimension of L square T raised to minus 2. This is the dimension of latent heat. Then we have coefficient of thermal conductivity. Coefficient of thermal conductivity, okay, which is denoted by K. But I'm not using this because there will also be dimension. Temperature dimension is K. So I will not be using this. So there is a formula. Heat energy equals Ka d theta T by L. Okay. So you know this is heat energy. Q is heat energy. K is the coefficient of thermal conductivity. A is area of cross section. D theta is change in temperature. This is time. This is length. Okay. Now we are pretty clear with what you need to do. You must rearrange this entire formula in terms of K. So K is equal to QL by A d theta T. So Q I know it is ml square T power minus 2. L is length again. So A is L square. Change in temperature is temperature basically. So K T is time is T. So L square will get cancelled. Therefore I am left with. So let me put a bracket over here because this is coefficient of thermal conductivity, or else we can just put a K dash so that we differentiate this with Kelvin. This is K dash, okay? So don't get confused with this. So we finally get our dimension formula to be M L T power minus 3 K inverse. This is our dimension formula for coefficient of thermal conductivity. Okay. Then we have Stefan's constant, which is denoted by sigma. So this has there is a formula Q by AT equals sigma T power 4. Again, Q is heat energy, A is area, T is time. This is Stefan's constant. This is temperature. Okay. Now it is pretty straightforward for you. So sigma is equal to Q by A T power 4 T. I'm just rearranging the formula, and now I can substitute the dimensions. So Q is heat energy, therefore I will substitute the dimension of energy, L square T raised to minus 2 by A is area, L square T power 4 is temperature power 4. So Kelvin power 4. Again, small t is time. So this is T. L square cancel. Now you get the dimension for sigma as T raised to minus 3, K raised to minus 4. So this is the dimension of Stefan's constant. Then you have Wein's constant, which is B. So again there is a formula, lambda is equal to B by T. This is wavelength. This is temperature. This is Wein's constant. So I'm just rearranging this. B is equal to lambda T. I've derived lambda, it is L, dimension is L. T is temperature, which is Kelvin. Therefore B has a dimension of Lk. Okay. Then now we are moving on to electricity. charge Q is equal to IT. Okay. So Q implies, so I is electric current. So this is charge, Q is charge. This is current. This is time. So electric current is so electric is also a fundamental quantity. It has a dimension A. You know this. There are 7 fundamental quantities. So electric is also a fundamental quantity with dimension A. And time is T. Therefore, charge has a dimension of AT. So then we have electric potential V. Okay. So V equals work done by charge. So this will, so work, you know, it is again ml square t power minus 2. By charge, we have right now derived it to be A T. From this, I can derive the dimension of potential to be ml square t power minus 3 A inverse. So this is my dimension for potential. We have electric resistance. There is this classic formula that you have learned in your primary, in your previous classes. So V is equal to IR, which is Ohm's law. Okay. So from this, I can derive the dimension of resistance. R is equal to V by I. So V, I've just now, electric potential, I've just now derived it to be ml square t minus 3 a to the power minus 1 by current. I know it is ampere again. From this, I'm getting the dimension of resistance to be ml square t minus 3 a minus 2. This is the dimension of resistance. Okay, now you might have a doubt. Why aren't we deriving the electric potential's dimension from this formula? V is equal to IR. Okay, I know what is the dimension of I, but I don't know what is the dimension of R, because we are using V's dimension to derive R. See, you can, in case if you know this before, R dimension before, you can do this. It is always fine to use whatever formula you like to derive the dimension quantity, because it is not going to change. Dimension formula for a particular physical quantity is not going to change. As you have seen before, whether F is equal to ma, or is it a viscous force, or is it gravitational force, the dimension formula force is never going to change. Then you have inductance. This is something new to you. This is represented by L, which is equal to RT. Okay. So resistance into time. This is resistance. This is time. I know now what is the dimension of resistance. It is ml square t power minus 3 a power minus 2 into time is t again. So I have ml square t power minus 2 a power minus 2. So this is the dimension of inductance. Electric capacitance. So C equals Q by V, where C is the capacitance, Q is charge, P is potential. You know both charge and potential's dimension. Therefore, C is equal to charge is IT, which is AT, by potential is ml square t power minus 3 A inverse. Ml square t power minus 3 A inverse. So from this I am getting the dimension of capacitance to be M inverse L minus L to the power minus 2 t to the power 4 A square. M inverse L to the power minus 2 t to the power 4 A square. Next, we have electric permittivity, which is denoted by epsilon. So there's a formula. F is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, where this epsilon is electric permittivity. F is force. These are charges. This is length, basically measurement of length. Okay. So now from this, I should rearrange this formula in terms of epsilon naught. So epsilon naught is equal to Q1 Q2 by F R square into 1 by 4 pi. Okay. So I don't consider 1 by 4 pi because it is a constant. So we are going to use this for our derivation. So epsilon naught is equal to charge is AT whole square because there are two charges by F is MLT minus 2 into L square. Okay. From this I am deriving epsilon naught to be M inverse. Then I have L to the power minus 3. I have T square T to the power 4 A square. So this is the dimension of electric permittivity. Then we have magnetic pole strength, which is small m. The unit of this is ampere meter. So ampere meter, from the units alone I can derive the dimension, which is going to be A. Meter is a length, therefore it is AL. So this is the dimension of magnetic pole strength. So let me just explain you like how to derive dimensions from units, SI units. So for example, let us take an easy example, force. So force is kilogram meter per second square. Okay. This is the SI unit of force. So kilogram is mass, meter is length. By, so in the denominator you have second square, which is time square. So by T square, which will give me MLT to the power minus 2, which is same as this. So you can either use formulas, define formulas to find the dimension, or in case we know the SI units of force, you can also use them to derive the dimension. Any ways is fine. So in the case of the magnetic concepts, I will be using units mostly. Then we have magnetic moment, which is capital M. So the unit of magnetic moment is ampere meter square. So from this I can directly write AL square as its dimension. So next will be magnetic induction or field. Okay, so the unit of this will be Newton per ampere meter. I know Newton is a unit of force. Okay, 1 Newton of force, 5 Newton of force. Therefore, I should write force dimension over there. So it is MLT minus 2 by ampere is A, meter is a length. So LL will get cancelled. I'll be having MT minus 2, A minus 1. This is the dimension of magnetic field. Okay. So then I have intensity of magnetization I or magnetizing field H. Intensity of magnetization or magnetizing field. Okay, so this has a unit ampere by meter. Therefore, the dimension is very simple, AL inverse. Okay, for both these quantities, AL inverse is its dimension. 38. Then you have magnetic permeability. Okay. So there's a force that is mu naught by 4 pi m1 m2 by d square. Okay, let me just explain. These are not masses, these are so small m in magnetics is magnetic pole strength. So the small m refers to magnetic pole strength. Therefore you should consider AL as its dimension and not capital M. You shouldn't consider it as masses. These are not masses, this is magnetic pole strength. So this formula is actually for forces between two poles. Is what this formula gives you. So this is pole strength. This is some sort of length. And mu naught is what is known as magnetic permeability. This is force again. Okay, if I rearrange this formula, it's going to be Fd square, 4 pi Fd square by m1 m2. I know 4 pi is a constant, therefore I'm not going to consider this. Therefore, from this I'm going to write the dimension. mlt minus 2 d square is L square. m1 m2 we have derived ampere meter, which is going to be AL whole square, because there are m1 and m2. From this we'll have mu's dimension to be ml cube t minus 2 by a square L square. L square and cube will get cancelled, so this is mlt minus 2 a minus 2. So this is the dimension of magnetic permeability. So we saw electric permittivity and magnetic permeability, both are different. Okay, 39th is going to be moment of inertia. So you learn this in your chapter known as rotational dynamics very soon, which is denoted by I, which is equal to mr square. This is mass, so capital M is mass. This is radius, which is length basically. Okay, so from this it is very simple to derive. It is ml square. So this is the dimension of moment of inertia. The 40th you have universal gas constant. So we know PV is equal to nRT. There's a formula in this sense. The P refers to pressure, V is volume, N is number of moles. I hope you understand my handwriting. So R is universal gas constant and T is temperature. Okay, P is pressure, V is volume, N is number of moles, R is universal gas constant and T is temperature. So from this I'm just going to rearrange this formula in terms of R. So R equals PV by NT. So pressure is M L inverse P power minus 2 if I'm not wrong, into volume is L cube. We have derived this already. N is number of moles. We also have a fundamental quantity known as the amount of substance, for which we will write it as mole. Temperature is Kelvin. This is like the most dynamic formula that you will ever see, because it involves temperature, mole, something that is new for you. So if I simplify this and finally write, it is going to be m L square P power minus 2 K inverse mole inverse. So this is the dimension formula of universal gas constant. Then you have as 41st physical quantity Boltzmann constant. Okay, there's the formula R equals NKB. So Boltzmann constant represented as KB. So KB is Boltzmann constant, N is Avogadro's number. So R is universal gas constant. You might have been aware of Avogadro's number in chemistry, maybe in class 9th. So from this, we rearrange this equation in terms of KB. So KB, what happened? So KB equals R by N. Okay, I know what is R. So KB equals R is ml square T power minus 2 K inverse mole inverse. ml square T power minus 2 K inverse mole inverse by Avogadro number has a dimension 1 by mole. Okay, which is mole inverse basically. We write it in this way, or just write mole inverse. So mole inverse will get cancelled. Therefore, KB's dimension will be ml square T minus 2 K inverse. This is Boltzmann constant's dimension. Okay. So with this, we have all seen almost 41 dimensional formulas for various physical quantities. So in case if you find this video to be valuable, and also you can share this with your friends so that they can also get to know what are all the different formulas that are there in physics and how to derive the dimensional formulas for all those physical quantities. So I'll see you with another video next. Thank you. Have a nice day.